Hello students, welcome to this lecture number 11 on the structure of the atom. In this lecture we are going to discuss the dual nature of the matter. So today's heading of the lecture is dual nature of matter. Or we can say is de Broglie's relation. Keeping in view of the shortcomings of the Bohr model, because Bohr model is not applicable for all types of atoms, it is only been focused on the hydrogen atom. So it was the necessity at that time for the requirement of a atomic model which will be applicable for all types of atom. That is the general version of the atomic model. That was the requirement at that time. In this regard, there is a two concept. Number one, that is the dual nature of the matter, and number two, the uncertainty principle given by the Heisenbergs helps to shape up the new improved modern atomic model. And in this lecture we are going to discuss this dual nature of the matter. It is one of the important development. This is K.K. Mukherjee in the Science with Mukherjee Sir YouTube channel. So in this today's lecture we are going to discuss the dual nature of the matter. In the year 1924, Louis de Broglie proposed dual nature of matter as the electromagnetic radiation. Means as the electromagnetic radiations having the wave nature as well as this particle nature, the matter will also have this dual behavior. He further clarified this statement that as the photon is having the momentum as well as the wave nature, the similar fashion electron will have the momentum as well as its wave nature. So it tells that the matter will have the wave nature when it is in speed. Suppose the mass of the matter is m. So mass of the matter is m, the velocity is that matter is v, and lambda is the matter wave, and the momentum is p equal to mv. Then de Broglie proposed this relationship between the momentum as well also as when he is relating the momentum, means he is also relating with the velocity of this mass. So he gives a very important relation, that is lambda equal to h by p, or this can be further written as h by mv. So this is a very important relation we must remember. that this is also called the matter wave. This is also called the matter wave, that is you are written here. Like the electromagnetic radiation have its own wave, similarly matter is associated with a wave. It is called the matter wave when the matter is in the speed. And this relation you can able to calculate from the dual nature of the electromagnetic radiation also. How? We know for the light. Light means it is a photons, right? So energy of the photon, suppose this is the energy E, and its energy can be correlated with its frequency of the radiation. This is the mu is equal to the frequency of the radiation, that we already know in our previous lecture. Frequency of the radiation. So E equal to h nu, we can say E is the energy of the photon. Another relation, this is suppose relation number 1. Then relation number 2, it is again a very important relation when we are expressing the energy in terms of the mass. When the mass has been converted into the energy, this relation is given by the Einstein. This is very, very important relation. When we combine these two relations, what we get? We get mc square is equal to h nu. And this as because we know mu is again c by lambda. Lambda is the wavelength of the light. Then we can apply this h by c lambda, and this by rearranging this we can have lambda is equal to h by mc, and this relation is valid for the wave, that is electromagnetic wave. That is electromagnetic wave. So what is there is no basic difference between these two relations as given by this de Broglie's relationship and this, where it is only, you can see here mass is the mass of the matter, here mass is the mass of the photon, here c is the speed of the light, where v is the speed of the matter. So you can see there is a correlation. When a body is moving with a particular definite speed, it is going to give a... Now, suppose we are moving from a particular speed, and as per de Broglie, there is the association with us some wave. But in the practical life, we could not able to perceive that wave. Why? That we will understand now. Suppose a body having the mass of 0.1 kilo moving having the mass 0.1 kilo and moving with the speed of 100 meter per second, then what will be is lambda. Lambda, we know this is a relation, and from this relation we are going to calculate this. M is 0.1 mg, 0.1 kilo, and it is 100. Means the lambda will be 6 into 6 into 10 to the power minus 35 meter. Now you can see the lambda is very, very insignificant in our practical life, because you cannot able this is very less wavelength. length of this wave is very less, 6.6 into 10 to the power minus 35. Now we take the example of an electron. Suppose electron moving with a speed of suppose 1000 meter per second. Then what will be the lambda? So what will be the lambda? That will be the 7.2 into the minus 6 meter. Now we can see the difference, and why this difference come? This is basically, this difference come, we can say that is due to the microscopic object, and the microscopic object having the very less mass, and that is why when they moving at a particular speed, that will going to give a wavelength that is very much perceptible, that you can able to detect this wavelength. But when that is for the microscopic object, that we can see this is a microscopic object, and you will see the lambda is very less. So we can write here so this conclusion you can draw for the microscopic object like electron, protons, neutrons, molecules, atoms. The significant is de Broglie's relationship is very much significant because of the very less mass. But for the macroscopic object, this impact you can see here, the wavelength is very less, that we could not able to understand. So de Broglie's relation is applicable, more significant for the microscopic object. Now we can understand that a scientist, that's Davison and James, they have make a experiment, and when they put the electron beam on, allowed to reflect some electron beam, from the experiment of Davison and Jarman, we can conclude one very basic thing, that electron have the wave nature. When a beam of electron is allowed to fall on this nickel crystal, and this reflected light is captured in a photographic film to see the diffraction pattern, it is found out that its diffraction pattern is just like the X-ray. Its diffraction pattern is just like the X-ray, and we know X-ray is the electromagnetic radiation and it have the wave character. So we can conclude that electron have the, so we can conclude that electron is having the wave nature. And we also conclude from another experiment that electron also have the particle nature. How? When we put some flow some electron to a zinc sulfide screen, what is going to happen in the zinc sulfide screen? There is a scintillation, and this scintillation is produced, that one electron will produce one scintillation, and this will giving the proof that electron is also the particle nature. So we understand that electron have both the wave nature and as well as the particle nature. So that comes in your exams in the de Broglie's relationship. One of the questions that come in your MCQ, that what is the wave number of wave produced by a electron in the orbit? This type of question asks. Then we will going to answer this question. Now, if the electron have the wave nature, if the electron have the wave nature, what is the number of wave produced? So number of wave is equal to the circumference of the orbit divided by lambda. Lambda, that is the wave associated with the electron. So circumference, we can say 2, this is 2 pi r, and this is the lambda. We know from the de Broglie's relations, h lambda equal to h by mv. So when we put this relation here, what we get? 2 pi r divided by h by mv, and this will give 2 pi r into mv by h. We know also in the Bohr's model, we know that mvr is equal to n into h by 2 pi. So what we will do here, you can see it is coming, you can just put this mvr value is here, that we will get the number of wave is equal to n. We just put the value here, mvr, and we will get the number wave is equal to the orbit number. So you can see that electron being a particle, it is also associated with some wave, and this is called the matter wave. Whereas in the electromagnetic radiation, it is having the electromagnetic wave. So what is the difference between the electromagnetic wave and the particle wave? That we can understand. We have to explore this. What is the difference? Difference is, number one, that is the electromagnetic wave. You can see that it is the wave which is having the electric field and the magnetic field. But in case of matter wave, it is not having this type of electric field or the magnetic field. Second thing, electromagnetic wave is radiated from a source, whereas the matter wave is just associated with this matter. It is not radiated from the matter. The speed of the electromagnetic wave is equal to the speed of the light, but matter wave is much less than this. So these are all the differentiation between the matter wave and the particle wave. That is all for today's video. In this video, what we have understood, we have understand that how the matter is also related to its wave, and it is much more significant for the microscopic matters like electron, photons, neutrons, but for macroscopic it has not such significant impact. That is all for today's video. Thank you very much for listening. If you like this video, you can share to your friends. Thank you.